to InstrumentsDirect. I'm your host, Brent Baird, with InstrumentsDirect, and today we are going to talk about the PT878 flow meter. And the meeting is in progress. Ultrasonic flow meters, for those people that are brand new to the industry, it's a marvelous technology. We're going to talk about how this technology works in a very brief. We're going to talk about the hardware that you get in most kits with the PT878. We'll touch on some basic programming, transducer installations, data collection, and best practices, and of course my invaluable comments of what to do and what not to do. Try not to make my mistakes. Ultrasonic flow meters, a very interesting concept. Most people don't understand it because they can't see it. It's all about sound. So let's use a picture that can demonstrate the technology. And my favorite story is a man in a rowboat. A man in a rowboat would like to cross the river. And so when he crosses the river, he's going to go across, but you notice on the left-hand side there, the flow is going from left to right. So when he crosses the river, he gets carried downstream to the other side. And because there's a current, it kind of pushes him downstream. It takes him a period of time. When he comes back across the river, he's going against the current. And it will take him a longer period of time to transit the river. The differential of time going across and coming back is the coefficient we would use to calculate how fast the river is flowing. The faster the flow rate, the greater the differential. So if we use the same concept on a pipe, in this case there, the man in the river is more the picture to the right here. We send a sound burst across the pipe to this other sensor. It's going with the flow. It'll take a certain period of time to get from here to here. But at the same time, we're going to send a sound burst from this sensor back across the pipe, but I'm going against the flow. It will take a longer period of time. The differential between the two transit times is how we calculate how fast the flow is going inside the pipe, not a river here. And if we know what the area is, it will calculate the volumetric flow, or say GPM. So we have a couple different configurations on the transit time device here. And the picture on the left is what you use most of the time where both of the sensors are on the same side of the pipe. In this case there, we ricochet off the back wall and come down to the sensor here. And we send a sound beam, we ricochet off this back wall and come to the sound beam over here. This type, by different brands there, this is the dual path or the V configuration you may have heard. And this is the single path or the Z configuration. So those two are most commonly used, and they are associated with pipe size. And we're going to get into that a little farther down the road here. Now, the ultrasonic transit time equation, the core equations are the same, but they have many more additions to the equation to make it a little more accurate, a little more user-friendly. But as you can see, what you get to use today, you have a final device with drop-down menus to do everything for you. Go backwards 10, 20, 30 years ago, we had a big black suitcase that you had to carry around, and you had to program all these different variables. And to look at the math behind it, and that's what I'm going to say, an ultrasonic transit time flow meter is a big math equation. And today's technology is doing more math, just like your iPhone's doing more computations for you, your portable ultrasonic flow meter is doing more computations for you. And the way that it works is we have a sensor here, and we have a sensor here, and we're going to put them on the outside of the pipe. And the neat thing about an ultrasonic transit time is you know where the spacing is before you even put it on the pipe, because you program the meter, and the meter told you to put one sensor here and another sensor there. And it can do that because this sensor, basically each transducer has a crystal in it at a specific angle. And that angle is part of the math equation. And each transducer manufacturer has different angles. So you can't switch Siemens with a GE and a GE with a Dynatronics and so on. Everybody has a little bit different secret sauce in the angle of refraction that it comes into the pipe. So they have a piezoelectric crystal inside here that they energize, sends a sound burst through a pipe wall. Well, we need to know what the sound speed of, say, this carbon steel or ductile iron pipe is. And then say we had a liner, we had a Teflon liner or a mortar lining, we need to know the sound speed of that. And then when it hits the liquid, a phenomenon occurs. It's called Snell's law. You ever put a straw in a glass of water and look at it sideways? It kind of looks like it's kind of chopped in half there. Well, it refracts the sound at a specific angle, and we need to know the angle. We need to know the sound speed of the liquids going through, and then we reverse that with the same calculations, and that's a lot of math. Well, in the old days, you had to participate that in some level, and now you're basically going to say to a drop-down menu, I have this transducer, I have this pipe material, I have this pipe size, and I have this pipe liquid, and I'm done, and move the sensors apart 2 inches. So it was very technical, and now not so much, and it kind of has a lot of more autopilots as it did before. Now, with every flow meter, there are certain guidelines and specifications where it works best. You may not have these all the time, but the quest is to optimize your performance to get your best accuracies, get your best numbers for whatever you're using it for. So step one, you need to have X amount of straight run of pipe. So nothing unique here. Most flow meters require the same amount of straight run of pipe. And so in this case there, what we want is a symmetrical flow profile where the flow is the fastest at the center and the slowest near the pipe wall. And you notice there's different elliptical shapes. They're called Reynolds numbers. What we're striving for is if you were to draw a center line down the center of this pipe, the top half of flow equals the bottom half of flow. So with that in mind, this scenario occurs when I have enough straight run of pipe here. So the generic rule of thumb for flow rates around 10 feet per second. After an elbow, I need about 10 pipe diameters. Put my sensor here. And then I need another 5 pipe diameters for the next elbow. If those situations occur, this is what it'll look like, and your flow meter will work at its optimum performance. Now, if I don't have enough straight run of pipe, we'll call that an asymmetrical flow profile. And in this case here, if I have flow going through this 90-degree elbow, notice I have a shorter distance and a longer distance. When the flow comes through this pipe there, I'm going to have a tumbling effect. And if I was to put my ultrasonic flow meter sensor right there, I'd probably get a fault condition or no information at all. I need to move downstream the 10 pipe diameters and put my sensor here, and now I will look like a symmetrical flow profile. Higher flow rates, I had 20 feet per second, I need more straight run of pipe. If I had 5 feet per second, I could get by with a less straight run of pipe. If I have a major obstruction like a pump or a butterfly valve or something that's really distorting the flow, I need more straight run of pipe. So hydraulics do play a role. You can't see all the time what's going inside the pipe. What do I do if I don't have the required straight run of pipe, which of course has never happened? The generic rule is go downstream 2/3 of the available footprint. So if I have 3 feet, go down 2 feet, put your sensor there. And that's a starting point, and we'll look at some ways to try to get around that if we can. So let's look inside the pipe here. So we have a picture of the 2 sensors, one on each side of the pipe there. We have our perfect flow parabola here. So our Reynolds number is perfect. It's fastest in the center, slowest near the pipe wall. We don't care how blunt it is. That's a function of what the flow rates are. Flow is going from left to right. So I program my meter, and then the flow meter will tell me that this sensor goes here, and this sensor has this spacing. And if I put them at this particular application, bing, I send a sound beam from one sensor to the other, line of sight, straight as an arrow, I get my signal there. We now have an optimum performing ultrasonic flow meter because the math is correct. Now, what if I don't have enough straight run of pipe? If I don't have enough straight run of pipe, my flow profile might be distorted. And if my flow profile is distorted enough, my sensor may not even see this signal over here. And if that be the case, I may actually have to do something which is called profiling the application, which I will have to move the sensor to find the sweet spot. Now, this should only occur in applications that I don't have the required straight run of pipe. Now, the trade-off here, rule of thumb is you put it and install it the way you're supposed to. Mathematically, you'll have the optimum accuracy of your flow meter. when I begin to profile the transducer to find the sweet spot, I'm now less accurate from the optimum position. How much inaccuracy? Can't answer that. It's a function of what's causing the situation. Could be a lack of straight run of pipe. It could be a chunk of something inside the pipe. You could have put the math in wrong on the pipe. The pipe may not be perfectly round. So you could be, a little bit or a couple percent or more off if you really move the sensor back and forth. If you got to move it more than a, quarter inch here, quarter inch there, half inch there, half inch there, then your accuracies are going to go up. If you have to move a couple inches, you got a problem, and you can have some really fuzzy numbers there. So yes, we get calls all the time. How accurate is the device? We said great. Then we get a call from in the field. They'll say, I just wanted to read. Well, then you may have to profile the application to find the optimum location. Now, should you have an application, do you have lack of straight run of pipe, the profile distortion may not even be repeatable. So I went out to the job site on Thursday, and I had 1,000 GPM on the pipe, and I had a short run of pipe, and everything, I had to profile the pipe to get a signal. Fine. I come back next Tuesday, and I only have 200 gallons per minute. Well, the full profile's changed again because of the lack of straight run of pipe. I may have to move the sensor again. So varying flow rates will change where the metering point connection could be if you have a short run of pipe application. Now, spot checking, which is going to do most of the time with your PT878, not so much of a problem. If you're going to leave it there for a day, week, or month for a flow survey, that could be an issue. So as far as the application itself, this is what usually happens on Monday morning. I get in the car and I drive 200 miles to do a flow survey, and I get there and this is the plumbing I have to work with. And they'll say, just put your flow sensor right here. Well, we've all had this experience there, and the answer is don't put your flow sensor there because you're not going to get anything. Rule of thumb in showing the performance of an ultrasonic flow meter, never show it working or not working on purpose. It leaves a stigma, so your end client or your end user is going to look at that and says, well, I just want to see it work. I know it's not a good application. This is an application where you would decline to put the meter on the pipe because it ain't going to work. So we need to measure flow in this application. No problem. Go upstream, go downstream. If you have an application that's important enough, someone may have to get the backhoe out and dig a hole to get to your straight run of pipe. So rule of thumb is you got a long flow survey, a long distance, a lot of effort to get to there. Talk about the plumbing or the flow hydraulics before you get to the site. It can save you a lot of time, and you won't have to take the rollades when you get there. A good application, even a perfect application, you may require to get some ladders or scaffolding to get to the metering point, and then you may have to actually remove insulation to get to the pipe itself. So even a perfect application may require a little work there. So you may spend more time on a flow survey prepping the application than you may actually be taking the flow survey. So if you've got a job where you've got to do test a building, an entire building there, you may have someone to go through and remove insulation and get everything set up before you even come with the flow meter. So you can spend more money on labor on the installation of the device than actually the field testing of the device, the prepping of it. So where does this technology work? Well, it's kind of magic, we said. You put a sensor on the outside of the pipe and it measures through the pipe. So what's going on inside the pipe? Well, an ultrasonic transit time flow meter as opposed to an ultrasonic Doppler flow meter can be confusing. A Doppler flow meter basically works like police radar, sending the sound beam and will bounce off your car and send a signal back. A Doppler flow meter sends a sound beam and bounces off a turbulence or chunks of stuff in the process liquid. Doppler flow meters will not work on a clean liquid application. And what do we define as a clean liquid application? So generically, ultrasonic transit time flow meters need no suspended solids. They're using time. So ultra pure liquids, jet fuel, deionized water, DI water, water, chill water, hot water, sewage, and that's the bulk of transit time flow meters, which is 95% of all your applications. I got sludge, oatmeal. I've got a quarry application. I've got mining application. I've got 10, 20, 30% solids. that's where you put your Doppler flow meter. Transit time flow meters traditionally work on ultra-pure liquids up to about 2% suspended solids, and there's the fuzzy number there depending on the kinds of solids there. So you heard me. If you've got everything other than sludge, then a transit time flow meter is probably the way to go, which is the bulk of your application. So any aqueous application, clamp on transit time flow meter is your guy. You can use it for water management, energy management, HVAC test and balance, chemical process, water and wastewater, irrigation, and the list goes on and on and on and on. There are some advertised clamp on airflow meters, but they're pretty much not for the world that you and I are in. They're for exotic high-pressure metal applications. So if you have a compressed air application, this is not the technology for you to use at this point in time. Wish it was. It's not quite there. So stick with your liquid application, especially with the PT878 and other variations of it. What do we use a portable flow meter for? We use it for the discovery process. And that means, how much flow do I have inside my pipe? Do I need to buy a new chiller? Do I need to bill somebody for more use of water? I need to monitor my energy use. Portable technology, clamp-on technology is a very, very, very effective way to do a discovery process to justify additional investments. Maybe you want to put meters throughout your facility. What's the flow rate? Well, walk through the plant and use your portable flow meter, conduct the survey, add the temperature sensors to it, do a BTU study there. Portable flow meters on the outside of the pipe can save you tons of money there. There's no holes in the pipe. There's no prep work, no drilling or anything like that. You're a self-contained unit. You're all set to go. So the technology's evolved that it's a commodity item. Anybody can be trained very quickly how to use the technology there. So it's a very handy-dandy tool in today's technology and very accessible. What I mean by accessible, you can buy this technology. It's relatively inexpensive for a portable device that does everything here. And you usually buy it and look in a minute. It comes in kits. You can buy the individual parts there. And there's a lot of legacy equipment there. There's some of the old PT878s there that people still have that shouldn't even be working anymore. They've passed the longevity from a design standpoint, so that kind of shows you the endurance of the technology of this particular brand there. So you can purchase the equipment, and now, as I said, user available. You can't afford to buy the equipment, but you can rent the equipment. So you can rent it by the week, you rent it by the month. So there's no longer a knowledge-based requirement. Anybody can be trained in a very short period of time. Anybody can buy it, and anybody can rent it. So economics and technology are no longer, a border that you cannot cross there. In this case there, you have user accessibility to the technology, lickety-split. So let's look at the technology. Well, it's a handheld device. It's the size of, say, a big voltmeter. And it has a wire stand on the back. You can stand it up the table you want. Most people doing spot checks there hold it in one hand and have the transducers in the pipe with the other hand there. Depending on the vintage that you have, the older devices have an IR sensor for communications, and in the last year or so, the newer models have a USB port. Yay, sensor across the top, so we can have a little bit better interface there. In addition to that, you can have an analog port, and here's the ports to put the upstream and downstream clamp-on sensors there. Transducers, we have a host of different transducers for this particular model, and the transducers are selected primarily by pipe size. And I think that's a defining point between the PT878 and the bargain brand meters that you can get from other countries there for $2,000. This is the difference between the men and the boys here, is multiple frequency transducers. Most of the budget price transit time flow meters are one frequency, usually around 1 megahertz, which doesn't work at all on small line sizes. And then the signal processing is not nearly as sophisticated as the PT878. The accuracies aren't on the same page, so it's not an apple-to-apple comparison there. The PT878 is a divine science that has a host of different transducers. Not so much as some other brands that are necessary. They do cross the line, so you can get by usually with one or two different sets of transducers. The 402 is the current design with a metal case transducer. If you have the old plastic transducers, if you have the opportunity when you're upgrading equipment, I suggest you go to this design. It works much better than the old plastic transducers there. The beam is more focused and the numbers are less fuzzy. Bad decision is to take your old PT8 or your new PT878 and take your old sensors from the PT868 with the plastic and the red and all the different transducers. So you're taking old and new and marrying them together. If you've got a PT878, use the current design transducers for your optimum performance. So the 402, nobody really defines the pipe sizes, but we've been doing this since 1977, so this is what we do here. The 1 megahertz sensor we use from 2 to about 26 inches. I have, you can install them up for larger line sizes. It's a function of the quality of the pipe. So generically speaking, this is what we do. When you go to larger pipe sizes, then we would consider the 0.5 megahertz transducer. Can it go smaller than 28 inches? Yeah, you can probably take it down to 10 or 8 inches, should you. But this case there, this might be a better device for short runs of pipe with a heavier solid content because it's a 0.5 megahertz. So go stick with the pipe size first. Then for uniquenesses, to get off the manual there, we can talk about some other things. The transducer, small pipe sensor, smaller footprint, and it's all one little package there. This is a 4 megahertz system that works from 0.5 to 4 inches. And of course, we have some more in the family there. It's a high temperature version, which is pretty much the standard now when you buy a kit. You get the high temperature guy as opposed to the low temperature small pipe sensor. And for your guys with really, really, really high temperatures, then we have the blade or the waveguide there. And this is an expensive puppy here. And you need to have your little strips of gold or silver or something to run the process under here to interface between the two. So take out your checkbook there if you're going to use this as a survey device there. So this is used a lot in some hot oils and diaphragm applications. So it shows you the integrity and expansion that you can use with the technology there. So should you have the core device there, there are some unique sensors for unique-like applications. The clamping fixture. The clamping fixture has pretty much been around for a long time. The old block and tackle method here, and then you get the standard clamp. The really big difference on the standard clamp is the ruler. You can get a 12-inch or 24-inch ruler, and of course you need to have the chains to match there. The magnetic clamping fixture is the same guy with a little extra space on the end of it there. So it is a big clamp. So if you have a lot of 12 or 18-inch applications that are all metal pipe-like applications, and you do them again and again, you may consider this. Things that you don't know about this, I said this is big, so it's this guy plus this on the end of it there. You can get a special carrying bag for this. Is the maximum temperature of the magnet. The magnet maximum temperature is around 140 degrees-ish. So if you got higher temperatures, the magnet doesn't work very well. So keep that in mind when you specify that. Cables, the factory OEM cables don't last very long, so we do have an aftermarket cable on the website should you need to have that second go around there. The meters are now sold pretty much as a kit. So you'll see the PTSYS, so you'll notice the on the websites and on the back of the data sheets, it's just another marketing method there. So you may not even see the PT878 numbers that much anymore. So PT-SYST is pretty much what represents the kits, and if you go to a data sheet, you can pick this meter with this transducer and so on. So let's take a look at the programming of this meter there. As I said, it's not that complicated of a beast there. You can get through without the operation manual. This is just a really short, quick run through some of the things that we would show to someone that's really not done this device before. It has a bright measuring screen. We consider this the home screen, and it's configurable. So you have all the different choices here. Here's everything called out on the display there. So basically, your quest is after you perform your programming, you should get your flow indication on the screen and not really have to go anyplace further. So to navigate through the different menu screens there in the PT878, we start off by pressing the menu button. And this will toggle the menu navigator head at the top of the screen up over here. And from there, you navigate via the arrow keys and press each thing nice and firm. And then to toggle off the menu head, you press menu again. So if you get into trouble, one of the first things that we'll ask you, are you getting a signal? And you said, no, I'm not getting a signal. And we may ask you to go to the Diagnostics screen there. And you can get there by pressing the soft keys across the top, the F2 button. It'll pop up Diagnostics. And the first thing you kind of look at there is, what is my upstream and what's my downstream transit time? And if one of them are out, it kind of tells you what the problem is there. And that's usually the most case there. The left hand's not saying hello to the right hand. And so something's blocking the beam, and many times there that's due to poor programming. And so as we program the device, take note of what to do and what not to do. So when we go in to the program, the first thing we're going to select is the transducers. And by this, we go to select the F1 soft key. And the setup menu, as you can see, is divided into tabs across the top here. And most applications require going through these different setups to program this properly there. So to start this up, we're going to select the transducer, and we're going to go to the drop-down menu. There we go. I told you. All drop-down menu there, and scroll it down to the transducer that you have. If you have an older model and you have a newer transducer, many times the firmware can be updated to accommodate that. If it is an ancient PT878, then sometimes you can't. So we need to take a look at the serial number or age of the device to see what you can and cannot do. If you don't have that function, you do have a special workaround that you can put any transducer regardless of what the firmware is. So we select the transducer, and the most common transducers today, as I said, you're going to see are the 401, the 402, and so on. So after we select the right transducer, then we will need to select the pipe. And see across the tab here, we're going to select the pipe. We've got a drop-down menu. Today we're working with stainless. And this is set up in metric, but again, you can program the meter to read in English, so whatever you want it to do there. You have two choices, putting in the pipe information or checking off the ANSI byte and using the nominal dimension. Now, this is the most common mistake. Garbage in, garbage out. So for example, if you put in, I've got a 3-inch carbon steel pipe, and the pipe OD is, well, it's got to be 3 inches. I just ask you, if you've been to the lumber yard recently, is a 2x4 2x4 inches anymore? And the answer is no. So if you checked off the ANSI box for 3-inch pipe, guess what? The OD is going to be 3.5. So if you're typing the raw numbers in there, put the correct pipe outside diameters there. We ship every meter here with an ANSI pipe chart book, or it's downloadable from the website there. Put in good data, you'll get good data output. So select your pipe size, select your schedule, and then after that, we're going to select if we had a liner. So the only time you're going to see a liner is if you had unique Teflon or Kynar liner, but that's more of an exotic application, and it rarely happens there. If you're in the municipal market, you might see a cast iron or ductile iron application that has a mortar lining, and their linings are usually 1.25 or double that, but 9 out of 10 times it's 1.25 is the liner. So you put that information there. Again, as I showed you, as part of the calculation. Then we go and select the flavor of your water or your liquid. And in this case there, we have a drop-down menu of many different applications. And so the question is, what degree of applications, how generic can this be? This is part of the newer technology versus the thing from 30 years ago. There is some functionality as an autopilot. And if you were looking at the diagnostic screen all the time, you will note that the sound speed of the liquid is actually changing from time to time. It's not a constant value. So it does fudge up and fudge down, so the autopilot function kind of takes care of that. So under most applications, probably 90% of your applications, you're going to be underwater. Generically speaking, if the sound speed is plus or minus 10%, there's really minimal to nil effect on the performance of the device. So for example, if you had a water and glycol application, you can go to the other function and you can break out the percentage of glycol right there. I got 30% glycol, and I get this kind of temperature there. And when you go through the whole math thing, if you had 30% glycol and water, you're going to find out that you're usually far less than 10% differential sound speed from just on water. So you feel free to primp away, not that much different. If I had 75% glycol and water, that would be greater than the 10%. So most applications, mostly water, if you have that choice. If you pick something too far of the picture there, you may get no reading at all. Now, here we need to select the method of the transducer. Are both sensors on the same side of the pipe or one on each side of the pipe there? So as I said, the V-mount will be done most of the time. Generically speaking, we do that method from 2 inches to 24 inches, and then larger than 24 inches is a candidate to do the Z-mount. Not always the rule, depends on the pipe conditions and the pipe quality there. I've done some V-mounts on 90-inch pipes before. But generically speaking, when you get an older, crusty old pipe there, you're going to lose your sound. The Z method is a much more powerful transmit signal because it's only going across the pipe and back. It's not bouncing off a wall and ricochet. When it does that, it probably loses half of its intensity. So keep that in mind for your applications. And then the meter will tell you what the spacing is. Again, this is millimeters, but if you program the meter in English, it'd be in inches there. This is the differential spacing from transducer end to transducer end. In determining the sites, we need so much straight run of pipe. If you read the operation manual, you will find out that there is no application in the world that has enough straight run of pipe to use it on. So as I said, just obtain to the generic rule of thumb, 10 and 5, when you have an elbow to elbow. If you've got some monstrous thing before, a butterfly valve, something like that, then a little bit more. So keep that in mind. That's probably your hardest obstacle. And installing the transducer on the outside of the pipe. I'll tell you, things have really changed in this side of the fence here on installation. In days of yore, people would come out with a grinder and a wire brush and sandpaper and all kinds of things to prep the pipe. Not necessary anymore. The rule of thumb is remove insulation from the pipe. Don't cut little cookie cutter holes. Remove a line and a complete circumference of insulation on the pipe. If something is loose on the pipe, a rag or a wire brush is all you need. You do not need to take the paint off. You do not need to take the rust off. If you rub it and it doesn't come off, that's fine. That's typical for most installations. Now, as far as the communication between the sensor and the pipe, we need an acoustic couplant. And basically, why do we need an acoustic couplant? We need something to transmit the sound through. Well, remember our friend in the rowboat? Well, he's changed his rowboat for a motorboat, and he's out on the lake zipping around, and you just want to go in the water for a swim. So you're standing in the water up to your waist, and your friend in the motorboat's in the distance, and you wave to him and say, how you doing? Then you jump under the water, and guess what? It sounds like the motorboat is right on top of you, but you know it's off in the distance. And that's because sound travels faster through a solid or the liquid than it does through the air. The transducer is flat, the pipe is round. We need a conduit to send the sound beam from the flat sensor to the pipe wall. So we put a bead of acoustic couplant. How much? Toothpaste on a toothbrush. That's all you really need there. We don't need to goop this thing up there. What flavor of couplant depends on your application. The PT878 comes standardly with a bottle of, let's say, liquid goop. And the goop there is great for applications that aren't too hot, aren't too wet, and I'm just going to spot check. If I'm going to leave this there for a day, week, or month, then the liquid goop will run out. In that case there, we need to use some silicone goop. And the silicone goop is just a little thicker gooey that ain't going any place under moist conditions. It's not going any place under warm, hot conditions. So you can use different couplants based upon the certain applications. If you're going to spot check, the liquid goop is just fine. If you've got a higher temperature, wet application, we have all different flavors of goop that you can use for your particular application. If you're mounting your transducer, then the rule of thumb is, it doesn't make any difference really if it's vertical or horizontal, but the two places I prefer not to mount a sensor is at the top of the pipe and the bottom of the pipe. You can have some aeration at the top, and you can have some debris on the bottom. So anything on the side is fine if you have that opportunity. So again, these are best practices. When you can try to get this, you may not always have that opportunity. So you had a subterranean pipe, and you get to the site, and the guy just dug out half the pipe. Guess what? You're on the top of the pipe. Well, the hardware is always an interesting configuration. I think people base too much on the hardware. It kind of helps you line up everything. So, I mean, it's just a block and tackle with a ruler on it. We'll get a call on a Friday afternoon for an emergency piece of chain to be shipped on Saturday across country so they can mount their flow meter. Boys and girls, this is a ruler and this is a strap. If you run into an emergency situation, a tape measure and a hose clamp will solve your problem. It is not the end of the world. This just lines it up nice and sweet, but if you have an emergency, a chain does not make the performance work, any less there. So same thing with the Z configuration. The Z configuration, the second reason you don't want to do it is not as fun to install because you can't see the other side of the pipe there. So you try V all the time until you can't get it to work, and then in the larger pipe size, you don't have an opportunity. What I do when I have a large pipe application, I mount one transducer on the side of one pipe about 3 o'clock. And so what I do, in this case there, I draw a line across the top of the pipe until I find my 180-degree line on the other side, draw a line from here to here. Then we measure the spacing from this point to this point. We draw another line there, and that's where you can strap on your mating transducer. We need a direct line of sight, and no matter who you talk to, you're going to get a different answer. But just imagine the beam, the diameter of a pencil. It's probably a little bigger than that, but that's what you're shooting for. Now, if you have a large HP pipe that's 60 inches and it's laying on the ground, guess what? It's not round. You're going to put the math in for a round piece of equation there, but you really have no choice. You may have to prospect to find this. You will prospect more often with this kind of mount because you can't see this, and there are other deformities to the pipe with giant, large pipes there. So it's not uncommon. You may not have to go to this plane. You need to go up and down this plane to find the sweet spot. So the single traverse is more powerful, but more difficult to do. And so you usually reserve it to larger pipe size applications. Now, the device has a logger, so if you want to leave it there for a while to collect data, I don't remember, like 100,000 data points here. So in this case there, we need to go into the log manager. And in this case there, we access the menu button by pressing logging. And then we're going to start up with a new log. And just like everything else, we're lazy. We don't download our data. You need to create the log name. So name it so something's relevant, so when you go back a week later, you know what you're looking for there. Now we need to set up the general log options. In this case there, we need to format and type. In this case, we're going to use linear standard functions, and this is easy read to the log file, and that's pretty much your default. So next, we're going to start up the start and end time there. So here, you notice here, I've got year, month, date, and in this case there, I need to have a start time and a start date. Give yourself some time to start the log there, not a few seconds there, because if you start the log after this, you may be sitting there with no log data. And the next step is, how much data do I want to take? So every time you basically log an interval, it takes a snapshot of data. So remember, you only got 100,000 data points there. If I'm going to leave it there for a month, you need to go backwards to calculate what you're going to log and how often. You could have too much data. So if you have a rapid changing application, do a 10-second log. 95% of all the flow survey logs that I see are usually logged at 1-minute intervals. Again, it's all a function of the number of logs that you have. We need to go in now and choose what we want to measure. So if we hit the measurement tab, you can select, I want to measure velocity, I want to measure flow, I want to measure total. Now, each one of those lines is considered a data point. So if I did velocity and I did volume and I want to do diagnostics, that's 3 separate data points. So factor it into your 100,000 data points. So we select what we want to log. We go in and we activate the log, and to confirm the log, we have this little Q button down here. So one of the smaller things to see, I need my glasses, but it's a little writing pencil. And you can see the art done here was also done by the same guy who did Nintendo back in the days. So things have evolved from that source software. So how do we get the data out of this guy? Well, depends on the flavor of the PT878. If your meter is more than, say, 2 years old, you probably have the infrared sensor on the top. And if it's a newer device, you have a USB port on the top. So the old infrared sensor on the top, what we need to do is we need to go into the communication option, and we need to make sure it's set up for the IRDA protocol. And that basically means the beam on the top of the PT878 is a little window, little red window, and has clear access to the IR sensor that's connected to the PC. We'll show you what that looks like in a minute. And under Log Manager, highlight the desired log in the upper left-hand window. Press Menu, scroll to the Transfer option, and just press Enter. So here we need to highlight the desired log in the left window of the Log Manager. Press Menu, scroll to the Transfer option, and here we go, we press Enter. And now the screen shows a message indicating that the PT878 is searching for an infrared device. This is where you're going to get caught depending on what you have in the way of hardware and other communication devices that you have. In the days of yore, when you use your communication ports for your Palm Pilot and other devices like that, that could be an issue. And there's a case where our Geek Squad here can help you fix your computer to do something like that. It's not the flow meter, it's your computer. So clear up your communication ports when you do this operation there. And then you can see here's a diagram of a typical IR reading interface device. This is plugged in the computer, and this is saying hello to the little window on top there. So this is a package that comes along, the IRD package to read this device, and as you break them, I think we still sell them as spare parts as well. So you need a clear path to read that. And now your PC will begin the upload of data. And now when the data is complete, you want to return to the Site Manager. The log files, I said, will be transferred to your desktop, and you can open up the PC using the Panalog Viewer or the Panalog software, and then in some cases there, if you want to, you can export as a CSV file or Microsoft format there. So as you can see, the data that you're going to have there, you're going to have a timestamp of date and time and the data itself there. So if you need to do any manipulation, export that to Excel or make it pretty, make a chart or graph, you're all set to go. The USB methods using the newer software, not the older software. So in this case there, the difference being it's a hardware plug-in. It's far less phonetically, not a good word, as far as communications. You don't have the Windows burps, if you would, so much with the IR. The IR itself, you know, as they keep changing Windows, there's always communication problems. If it doesn't work today, try it again tomorrow, kind of thing. So we power up the PT878 and connect it to the PC using the USB. We verify that Windows automatically loads the driver. We verify completion of the driver installation, and then we open the control panel on the Device Manager window and select the ports. There's a picture here to the right on your computer. So make sure that PT878 US port is installed. So again, using the USB method, we need to set up the drivers. So open the USB setting port windows and match those listed in the PT8 communications window at the PT878 user interface. And note this case there, the COM port settings may vary with the PC configurations. So here we are using the PanaView setup procedure. And this again, this you used to have to buy, and this now comes with the new PT878. And so in launching the PanaView, we need to select File, New Meters Browser, and we need to expand the network and right-click on the computer icon, which is located just before the network icon in the Explorer window. We select New Communication Port to open up a window similar to this picture. And we need to program each COM port parameter to match a corresponding PT878. The protocol COM port should remain as PanaLink and RS-232 respectively. Make sure the COM port matches the PT878 USB COM port as we talked about before in the USB setup. So here we need to right-click on the COM port icon and select New Meter. On the first screen of the Add New Meter wizard, you need to select, I don't know the node ID of the meter I'm adding to the network, and click OK. On the second screen is the only meter connected to the COM port, and if OK. If the meter is found, a screen similar to the picture on the right will open. If it doesn't find it, time to go to lunch. So here, we need to enter the name and the serial number and click OK on the next screen. Serial number you'll find in the back of the flow meter. See picture to add PT878 as a new meter. The PanaView will automatically upload the required system parameters into its database. And the PanaView setup is now complete. So connect your PT878 to the PC. View the available logs from the PT878 in the meters log section of the PanaViewer Explorer window. It'll look something like this. Double-click on the log file and the data will be pulled in to PanaView where it can access it in the meter log screen. The data then can be displayed as a graph and saved as a PC log file if you like to. The PC log file can also be exported again as a CSV file and opened up in Microsoft Excel. Now, the thickness gauge. The thickness gauge is an option. Some people use it, some people don't. Let's get down to the reality factor of the thickness gauge. What is it measuring? A thickness gauge is designed to monitor and measure your continuous measurement from the top of the pipe to the inside of the pipe as long as it's a metallic material. If you have ooey gooey on the inside of the pipe, your goop will not be measured by the thickness gauge. If you have 5 years of calcium buildup on the inside of the pipe, it will not see the calcium buildup. It's monitoring, for the most case, the metallic, the rust, and the material, and probably the paint on the outside of the pipe, the thickness gauge. So most cases, the ANSI pipe chart book is more than enough to measure your pipe. The thickness gauge is very helpful in applications that are older pipe where there's wear inside the pipe. And it's great for monitoring stress pipe and pipes that do need some services. So very good for that particular application. Less and less popular as a flow meter tool. ANSI chart usually suffices it. But if you have one there, here's the transducer method. You go ahead and plug it in the top of your flow meter, and from the transducer menu, select Pipe tab, and then confirm the appropriate pipe material is selected. So once again, we need to know that they put in the right material there, so I can't just say steel all the time if I got a copper pipe. So every sound speed is different, and it works accordingly. Put in the wrong data, and you get the wrong answer. So from the Pipe tab, then highlight Measure Walls with the thickness gauge, and then press Enter. And now we're going to install the device. So in this case there, we need to put your thin sonic couplant. This is not an application where you want to use your silicone grease. We're not talking because of just the thickness of it. We want to have metallic contact to metallic contact. It's just a small film of transferring the sound from the face of the thickness gauge to the pipe wall itself. So the key is apply your couplant to the face of the thickness gauge, press it on the pipe so you have a mechanical contact there. Don't wick it up. Don't squeeze it up, pull it away from there, because it may also see the sound beam through the wicking, if you would, and the pipe wall thickness, and it could give you an erroneous reading there. Another thing to consider, the thickness gauge does not work in high temperature applications. My recollection is it's good to up, I remember now, 104 degrees. Don't verify me, so I have to look in the manual there. Don't leave your thickness gauge in the trunk of your car in Miami for a month, because it'll get too hot and it'll toast it. So keep that in mind with the transportation of your thickness gauge. Energy applications. Well, some people will like to use this for flow and energy. If you have an energy application, you can't beat this for getting survey information from a log to manage your chilled, your hot water, your cooling application. Do I need to put the new chiller in there? To make a dynamic impact on the use of other technology by doing discovery process with doing an energy survey. So what do you have? Well, you got the same PT878. Now we need to add temperature. So in the I/O port that we'd normally put 4 to 20, we would plug in our temperature kit, which is basically 2 strap-on RTDs. Now, we basically give you the RTD, you get some couplant, special thickness goop we put in here for temperature heat transfer, and you get to strap it on the outside of the pipe. And then they get connected to this Y connection, and that gets plugged right into the PT878. So this is an optional device there. Strapping on temperature on the outside of the pipe is an important point that you need to get over. Customers will say, well, it's not wetted, so it's not exactly the same temperature as it is on the inside of the pipe. When calculating BTU, the key point to the equation is temperature differential, not exact temperature. So the reason these strap-on RTDs cost so much is they are precision calibrated matched pair RTDs. And so when you put them on the pipe, there will be better than 1% when you put them on the pipe. So that's the key to the success of any BTU applications. And in doing that, you need to install the temperatures on the pipe correctly. So in this case there, if I was to put one on the supply and one on the return line, one at 6 o'clock and one at 12 o'clock, I could have, the heat would rise here, I could have a couple of degrees temperature on this application. What I need to do is I need to have an apple and an apple, same to same. So if I'm putting them on the pipe, put them in the same position. Put this on a 3 o'clock and put this one at 3 o'clock. And so the temperature differential between these two are insignificant. A couple degree temperature differential can make a significant effect to your BTU calculation. It's all about the temperature. You already got the flow covered there, so install it properly and you get good data. So to set up the temperature guy, we need to go in and set up the screen for temperature. We select the measurement screen for reading temperature, and we go this by targeting the main screen and pressing enter. And from there we select, guess what, temperature. And from the option we press select key to choose the type of temperature option. And in this case there, before we use the temperature feature in the PT878, we need to set up the energy analog inputs. So here we go, and we press menu, we select program and energy. And then we press enter. We begin on enabling the energy options. From here we choose heating and cooling and supply and return. So now you're identifying one temperature sensor is for the supply, one temperature sensor is for the return. So when you get your data, everything's all boxed up accordingly, so you can go reverse backwards and find out what's going on. Keep your calculation methods on standard. And then we need to move into the input tabs. We need to activate both the supply and return on the input. This is the data you're putting in. And once we're confirmed doing this, we hit OK. So the second part of the step involves the analog input menu. We need to press analog input, press menu, then choose program. There we go, then press analog input. That's okay, I've only done this a million times. From here, continue the analog input A and B, are supply and return respectively. We set the temperature and span of both inputs. We hit enter. Now you can monitor temperature. How about that? A lot of information, short period of time. My speaking is much longer than it will obviously take you to program the flow meter. The flow meter is much smarter than I am. So what did we learn today? This is a tool. This is a very popular method of technology that you can do discovery, you can do flow survey, and you can do dedicated flow monitoring with this device. We learned about the theory of operation, where this type of technology works. So basically any aqueous application that's ultra clean up to chunks of stuff is designed to work with an ultrasonic transit time flow meter. Get me some straight run of pipe if you have the choice. If you don't have the choice, the best thing you can do is go downstream 2/3 of the available footprint and try it there. There may be some applications that you will not get a reading because you don't have enough straight run of pipe. The meeting will fault out, you'll get no data. But bad data is just as bad as you just don't want that. You'd rather have no data than bad data. We talked about the hardware. We talked about the different type of transducer and the method of transducer installation. And of course, we talked on how to harvest the data. So, with all that said there, what do? InstrumentsDirect has been around for a very long time, and we sell and distribute and service and calibrate all different flavors of ultrasonic flow meters. So we have a good reference point of how the PT878 fits in that particular world there. So we're an engineering group in the world of ultrasonic flow meters, and our sister company, Non-Contact Meters, and manufacture some dedicated ultrasonic transit time flow meters. A lot of things we talked about today will be on the website here. So if you want to go to the website, you want to see a video, this thing that we're doing right now will be recorded. We'll drop you an email and post it, so you'll be able to get a copy of this webinar, again, at your convenience. So I have gone long over my time, which never has happened before. It happens every time. So what we're going to do is we will conclude the audio portion of my program. We will leave the chat function open for a little while longer. Should you have additional questions regarding this webinar about the PT878, feel free to drop us an email or give us a call. This has been Brent Baird for InstrumentsDirect.